All right, cool. It's time for our second last talk of the day. I have good news. Our 4:30 talk is in fact going to make it, and we might even have a bonus talk after that. Oh no, maybe not. It is happening. Okay, he's here. He's got quite a story. We'll wait until 4:30 for that. Our next speaker is Mobile Research Team Lead at Checkpoint. Really big fan of fuzzing. He presented some cool research at DEF CON last year, and he's here to speak with us about his latest research. Slava?
Okay. Hello, everyone. Today I'm going to talk about trusted execution world of mobile devices. The goal of the research was to build a fuzzing platform to test reliability of Qualcomm trusted applications. Why this subject caught my attention? First of all, trust zone-based environment is the most protected part of mobile device. Therefore it's very interesting subject for security research. Such critical features as key store, security storage, authentication, rights management, mobile payment are parts of the trusted execution environment. Besides, there is very little public research in trust zone application area, and there is nothing in the field of Qualcomm trusted apps fuzzing. So what is trust zone technology itself? Trust zone is extension integrated by ARM into CPU. This extension creates an isolated, secure virtual world which can be used by the main operating system. Actually, ARM integrated the concept not just in application CPU, but in several system-on-chip components, including RAM, bus, and many other controllers. In the context of the current research, we just need to know the following. Application CPU has two modes, normal and secure. Operating system like Android, including Linux server, runs in the normal world, and trusted operating system, for example, implemented by Qualcomm, runs in secure world. Normal world doesn't have access to memory of secure world and communicate with it using special secure monitor call, SMC, CPU extraction, and it. But trust zone technology is just a technology, and CPU manufacturers have to implement a software, trusted execution environment based on the trust zone. And there are three most popular TEE for mobile devices: Qualcomm Secure Execution Environment, or shortly QUC, integrated as well as Qualcomm CPU in LG, Xiaomi, Motorola phones, Samsung devices for USA and Asia market. High silicon trusted core could be found on most Huawei phones, and Rastronic can be integrated in Samsung devices for European market. Qualcomm covers more than half of mobile market share, and I focus my attention on Qualcomm. Let's take a look deeper at Qualcomm TE on QC. And in Android framework level, QC presented by libqc.com API SO library, which implements a high-level API for communication with secure world. Linux kernel contains QC.com driver, which redirects all normal world requests to secure world using SMC instructions. Qualcomm OS, or QC OS, as well as trust zone kernel implemented by Qualcomm run in a secure world, and actually we can look at both of them as on one operating system, and both of them represented by a single executable file. The top component of secure world is trusted applications, trustlets. They are target of our research, and trustlets contain business logic of mobile device security. An example of interaction between normal and secure world is when Android service ask a specific trusted application in secure world to, for example, decrypt streaming, media streaming. And one thing that I want to mention is that Android restricts applications and services which could communicate with secure world. Only DRM RPC group can access QCOM driver. And here I listed several Android services which have such access. So we need a binary for reversing. Where can we find QC binary? Actually, all TE components could be either extracted from ROM, firmware, downloaded from the internet, or pulled from a device itself. In our case, only QCOM driver is open source. Other components are proprietary. So let's take a look at the flow where Android program loads a trustlet in secure world and send a comment to it for processing. In this flow, I want to show my way to find a special function in trusted OS, which is responsible for verification of trusted applications. So libqc COM-API SO library provides an API for loading a trustlet. There is function for loading of truslets by name. There is function to send a comment to load the trustlet. Actually, this library redirects API requests to QCOM driver by using specific IO octaves. What is next? As I mentioned, QCOM driver uses special SMC CPU extractions to enter the secure monitor and redirects execution to secure world. Actually, this driver fills some structure which will be used as a parameter for SMC call. Here I marked with arrows two fields in these structures. The first is API comment ID, which means load a trustlet or send a comment to trustlet or maybe something other. And the second ID with value 3F001, it's ID which refers to handler of SMC call in security in trusted OS. The next step in the flow is to find a handle in trusted operating system which will process, which will handle normal world requests. For this research, I dumped Trust Zone binary from Nexus 6 device because there is one interesting feature. It's known bug in the binary, which I use later in the talk. This bug is that one of code segments is unprotected by hardware. So let's back to our flow, and we are going to locate some handler in trusted OS which will process all SMC extractions. For this, I just need to search 3F001 dworld in data segment of the trusted OS, and in this case I will find a specific entry in so-called secure channel manager table. Each entry in this table holds ID, name, and pointer to handler function. In our case, in this table, we see that Trust Zone BSP exec SMC function will be called for process all SMC requests from the normal world. And in case if parameter indicated in SMC call is 8, which means to load a trustlet tab, exec SMC function will call another function, QC-load and auth-elf image. Actually, this is target, my target in this flow, because this function is responsible for verification and loading trusted apps in the secure world. And we will look at this function in details when we will talk about trusted verification algorithm. So here is an example of Android program which loads prof trustlet from firmware image directory in Android and send some comment to it for processing. Here I want to pay attention to API function for sending a comment. This API function requires two buffers as arguments. request buffer, which contains specific command for prof trustlet, for example, and a result will be returned in the response buffer. All trustlets behave in this way, and the request buffer can be abused by attacker. So what is the trust on Qualcomm application? Qualcomm application is signed ELF file. It's a regular ELF file, but extended by special hash table segment. This segment contains SHA hashes of all program segments and ELF header itself. This hash block signed using certificate chain, and QCOS validates just root certificate using using key burned into one-time programmable if used. In Android file system, the trustlet ELF file split into several files. Each segment is saved in special bx6 file, and MDT header file is just concatenation of B00 and B01 file, and it's enough to concatenate all bx6 files sequentially and to receive correct ELF file of trustlet. Here you see several examples which could be found, examples of trustlet apps which could be found on Nexus 6 and Samsung N7 devices. So let's take a closer look at trustlet code. I found actually we need to find some function which we are going to fuzz. And there are three major functions in each trustlet. Start function at offset 0 will be called by QCOS after verification and loading of trustlet in the memory. And in this function, trustlet register itself using -100 syscalls and providing stack address, name, and pointer to a specific handler function. Okay, this indicated here handler function will be called by QCOS after trustlet registration. And in handler function, trustlet first of all perform initialization, and then each trustlet can be linked with special trustlet with name CommonLib. Actually, is CommonLib library, which contains command code, and one instance of CommonLib trustlet can be linked with all trustlet in the system. If our trustlet want to use common library, you just need to call function at offset 0 from the common library, and it will fill its import table. The last part of the handler, handler function, it's a common listening loop. Trustlets waits for command from secure world, from normal world, sorry. And in the case when a new command will be received, another function, common handler function, will be called, and Trusted OS provides passes request and response buffers from the normal world exactly in this function as arguments. Actually, it's this function we are going to fuzz, providing permuted data in the request buffer and analyzing code coverage for each test case. Let's take a look at trustlet memory. The system reserves special setup region of physical memory, which will use for location all trusted apps. Start address and size of this region could be easily found in kernel log of Linux, and trustlet is isolated from the rest of the system, and it doesn't have access to memory of another trustlet and except common library. And there is only one way to communicate with secure world. It's by using of syscalls. One interesting thing for this research is that trustlet heap and stack regions are part of the trusted data region. It means that any location in memory requested by trustlet will be performed exactly in data segment of the trustlet itself. And if we want to dump the trustlet from secure world, we just need to dump its data segment, and that's it. So now we know that trustlet is L file. Let's try to run it in the normal world on Android. Because if we can run it, then we can fuzz it. But what does it mean to run a trustlet in secure world? We just need to dump its data segment and data segment of common library from secure world, and then implement specific trustlet loader program in Android, which will allocate dumped data in its virtual memory and code segment of trustlet in its virtual memory as read-write executable. Then points R9 registered to trustlet data because it's some feature of trustlet code, and at last call command handler providing some request and response buffers. Looks good, but we will fail on the first syscall because Linux kernel cannot recognize Trust Zone kernel related syscalls. And actually we have two big problems here. The first is how to dump trustlet from the secure world, and the second, how to process all syscalls related to the Trust Zone. And the solution is to load a paged trustlet instance in secure world and make it do the work for us. In this case, trustlet loader program can ask page trustlet in the secure world to return its base address, to dump itself, or to invoke syscall. And we just need to put our handler for a specific command ID, for example, 99 in trustlet code. And in this case, our handler, like debugger, will return for us data segment of trustlet before execution in normal world and execute syscalls during execution of our trustlet in normal world. And but how to redirect all Trust Zone related syscalls from normal world to secure world? Actually, I used QEMU emulator as channel between worlds, and I just extended code QEMU in the way that we will catch all syscalls related to Trust Zone, and using Regular Qualcomm's API, will redirect these syscalls to page trustlet in the secure world. Actually, all communication scheme will look like following. We have the trustlet loader program over QEMU on Android device, and this trustlet loader, before execution, requests from paged trustlet in the secure world to return its data segment. Then trustlet loader execute original code of trustlet extended by dumped data, and QEMU emulator will redirect execution of all syscalls to paged trustlet on its behalf. This scheme will work. All just left to do is to find a way to load page trustlet in the secure world. To achieve this, we need to find a way to bypass Qualcomm chain of trust. Android security boot, it's when primary bootloader of device verifies integrity of secondary bootloader verifies integrity of Trust Zone image, actually it's our Trusted OS. Trusted OS verify integrity of all trusted apps on loading. There is no way to break this chain without an exploit, and I used to well describe it one-day exploit, which allow to write in QC memory in case if it's not protected by hardware. And my goal was to use, for example, to this exploit to break trusted verification implemented in Trusted OS. Let's take a look at QC-load and auth-elf image function, which I mentioned previously, which is responsible for verification trustlets on loading. The verification algorithm consists of two parts. The first part implemented in kill-init image function, which going to parse hash table segment of elf file and then validates hash block signature. After that, another function, kill-init auth reset function, will calculate actual hashes of all program segments and validates and compares these actual hashes with validated previously. And I implemented some payload which will overwrite hash block of elf right after its verification and before comparison with actual values. This code of kill-init image function. Here we see, here I marked two global variables. First of them is base info object, which actually holds all results of hash segment parsing. And after that, in this function, this base info object will be validated. And in case if signature is correct, another variable will indicate, okay, we have finished, everything is good. On the right side, this is my payload, which I used to overwrite base info object. After verification, we could inject this payload in unprotected by hardware map region function, and QCOS will call many times this function exactly after signature validation of trustlet and before comparison with actual hash values. So putting it all together, what do we have? We have vulnerable wide wine trustlet in secure world, which breaks signature verification using our payload. We have our patched trustlet in secure world, which will return dumps of memory from secure world and execute syscalls for us. And the last part, we have trustlet loader Android program, which works over QEMU emulator on device, and this trustlet loader will call common handler when we want it. All just left to do is to find some fuzzer for Android and to use it to fuzz, and providing some permuted data for trustlet loader. And in this research, I used famous American fuzzy loop, and because it could be simply integrated with QEMU emulator, which we used as a bridge between worlds. Okay. We built working fuzzing platform on Nexus 6 device. But what if we want to fuzz trustlet extracted from another device, for example, from the latest Samsung S10? Yes. In this case, we need to adopt external trustlets for fuzzing on Nexus device. And I will show, will only touch briefly what I did to adopt. First of all, the certificate chain of external trustlet could be incompatible, and in this case, I just replace hash table segment of external trustlet by a suitable one, extracted from example, from prof trustlet from Nexus device. Modern trustlets could contain several data segments, but Nexus-related QC expects to see only one. In this case, I just merge all data segments in one, and that's it. New trustlet code assumes that its base address in the memory is 0. And we need to, in this case, we need to fix all X reference in read-only data segments of the trustlet. And this is just example of simplest IDA script which I used, which find all X reference in data segment of ECCOM trustlet from Samsung device. The last thing which I want to mention here is just start and handler function of trustlet. Requires some minor fixes as well, and but it's always something specific to trustlet. So after this long and hard way, we made to the point that we can fuzz Qualcomm trusted applications. Let's just look at several results which I have. And first of all, it's really cool. The sending of 32 bytes to a specific trustlet on Samsung device will crash biometric authentication on all Samsung devices. But the goal of the research was not to build an attack or an exploit, but to check how reliable trusted OS, which is supposed to be the most critical part of mobile device. And in this research, I just took several trustlets implemented by Samsung, Motorola, LG, and Qualcomm itself, and found vulnerabilities in all of them, and including Samsung S10 Plus. So that's it. Thank you for your attention. If you want to know more about our checkpoint research, these are coordinates. Thank you. If you have any questions.
Hi, thanks for the talk. If you needed to compromise the trust zone either way, why did you have to run the trustlets, to fuzz the trustlets in the normal world?
Okay. First of all, I just want to emulate trustlets, because okay, we have a lot of fuzzers for black fuzzing. It's mean black box, just sending random data. I want to use something very smart and to use feedback-based fuzzing. It means that I want to send some test case, and I want to see coverage of code. For this case. For that, I need implement some emulation. Here we have emulation based on QEMU emulator, but I can run QEMU emulator in trusted world. This means that I need to get ELF of each trustlet and run it in its normal world. And that's it.
What is the disadvantage of, instead of doing all of this crazy cool stuff, simply fuzzing via the QCCOM driver, via the interface that's provided, assuming we can escalate our privileges such that we can use the driver?
So I don't understand the question, but why do we need it, yeah? So, okay, each trustlet implement some specific critical feature. Mobile payment. How to attack mobile payment? In this case, I just need to attack trustlet itself. It's very simple. I just need to send some buffer to it for processing. And in this case, it's supposed to be that this trustlet is responsible for mobile payment will be so hard that it's and this means that attacker could not attack it. But fuzzing explained me that no, it's a lot of trustlets implemented by several brands, not just by specific Samsung. All that I have, all that I try to fuzz in all of trustlet, I find vulnerability. And this means that developers of trustlet could pay attention on this during implementation. Thank you.